Welcome back, folks. We have maybe one more day of CFA, maybe two. We'll see how it goes. We have the second half of the steps of model fit to talk about still, so we'll see how well this goes. You don't have anything due on Monday, so you get that break. I don't have your next homework up yet, but I will let you know once it is available within the next couple of days is my goal. And I will put up homework 3 probably around the same time so that you can start planning on what you would need to do with your item level data. Hopefully by now folks have identified data that they want to work with and maybe have obtained it, maybe not, but you have a few weeks until that's due, but just to give you the heads up on that. So we were talking about last time the idea of global and local fit. Broadly construed, what is the difference between global and local fit? And feel free to use the words as the basis for the start of your answer. Global versus local fit.
Global would be kind of like the multivariate wall test for this thing, where you instead you just check for the variance and covariance.
Yeah, I like that. It's kind of a multivariate test. It's sort of like the whole thing at once. But looking at the whole thing at once means that specific problems could get washed out if most of it looks fine, which is why then we have the local fit. So local fit is either like localized strain is what it's called, or local misfit. But it's the idea of going into detail and looking at every specific element to be recreated, every item mean, every item variance, which both of those are usually fine, and every item covariance to see how well the model has recreated those. And if it's recreated well, then you have evidence that your factor structure is reasonably correct. And if not, then you got to figure out what happens. So global indices of fit, then, they come in basically 2 flavors. How much worse is your model than perfect? So that's your chi-square test of model fit, which is a likelihood ratio test of your HO model relative to the perfect H1 saturated. There's also RMSEA, which the best it can be is 0. It's how far off you are per degree of freedom remaining, so it's a parsimony corrected index. And SRMR, which is the average offness of your correlations. The other flavor, do you remember the other type of fit index that there are? You can give me the acronyms or what they do, your choice. CFI is one of them. Other acronyms you remember?
One with a T?
One with a T, that is correct. Or one with an N, I would take. Yeah. TLI is also known as NNFI, depending on your software. And what do they have in common? What do they assess? Your model versus what?
The null model, right?
The null, the worst you can do. So the CFI, TLI, yes, the Zoomer's correct. The one that it's the best you can do is 1, except for the TLI one goes above 1. That's why it's non-normed, is the NN part. The idea is how much better did you do than the worst possible model? So ideally you would pick a index from each type at a minimum, if not all of them. Typically what you would see is if you have a bunch of different models to report, you would make a table, like the one that's in the spreadsheet that goes with this example, where you would table all of your fit statistics and then just use words to describe, what was acceptable and what was not acceptable. How do we assess local misfit or local strain? What do we look at? The element by element inspection. Where do we look for that? Our keyword starts with an R. Yeah, residual something. It's residuals for covariance, not to be confused with residual covariance. A residual covariance is a relationship between the not the factor parts of an item. Residuals for covariance are the local fit discrepancies. So in M+, that's what you would look for, is the residual output. In R, it is, object is like fitted or something. I'm trying to remember the exact terms. Yes, in R, it's so the model predicted version is fitted. That shows up as the first part of the residual output in M+. And then there's a resid function where you can ask for raw, which is in covariance metric, core, which is in a correlation metric, and then normalized, which is like z-scores, where you want to look for large values in an absolute value for that. And for these, what if you see positive numbers? What does that tell you? Yeah, they're more together in the data than what the model says. So you're missing something that's causing them to be related to each other. It's not in the model yet. And what about negative values for these discrepancies? Less together. Yeah, and that's harder to fix. You'd have to probably move them to separate factors somehow to be less together, which is difficult if you only have a single factor model. So that was where we were ending last time, I think, is sort of talking about different ways to add things to the model to make it fit better and how that corresponds to different theoretical statements about the dimensionality of your items. So I think that's the big picture that I wanted to review. Any questions or things that you want to hear about in greater detail than that? No? That's fine. The answer is no, that's fine. We have one no, several people staring at their tablets, no one typing in the chat window. Should I assume that no responses means no? Done. Moving right along then. Yeah. Let's see. So, so local strain. Along with that, the idea of modification indices, I'm picking up on slide 63 here. So these are what I refer to as cheat codes. These are ways to improve fit that are capitalizing on the problems identified in the discrepancies. But the key thing about these is that they don't care what they mean. Like, this is just literally a data-driven, make these two things related and it'll fit better. It's up to you to, as I have in capital letters here, to be able to interpret and defend your choices. So you would never want to add these suggestions unless there's a reason that you can come up with why it makes sense to do so, and that you would expect to replicate in additional samples. Another caveat is that you would want to implement them one at a time, because the list of the suggested changes will change after your model changes, because then all the predictions will change going along with it. So testing fixes to the model. So anytime that you are comparing alternative versions of your model, so different types of HOs, remember, you are the HO. So if you want to know if 2 factors fits better than 1, for instance, that's a comparison you have to do yourself. That's not going to show up on the output for you. So you can either pull out my spreadsheet and type the numbers in to do your rescaled -2 log likelihood test. You can use ANOVA in R if you're using Lavon. And I don't know if the LR test works in Stata for this, but I have a suspicion that it probably should. Here is the language on the M+ website, by the way, that describes this test. Here is the formula presented more formally. Like I said, I built a spreadsheet for this. The big difference is that it's not just a function of -2 log likelihood. You have to compute this additional quantity to rescale it, where this becomes 1 if you're in straight maximum likelihood, and it's some other number if you're in the robust version. So in terms of how to talk about model modifications, if you are adding a parameter to the model, so if you want to go from 1 factor to 2 factors, in which case you are adding a single factor covariance, or if you'd go from 1 factor to 3, in which case you're adding 3 covariances, or if you want to add a error covariance, then we would talk about the results of the test as either making the model better if the test is significant, or not better if it's not significant. The other fit indices could get better or they could get worse because they track different things, but in terms of just the likelihood ratio test, chi-square test, if it's significant and you've added things, it makes it better. If you're going the other way, so if you think that you have this lovely 2-factor model and you write up your paper and say it's a 2-factor model, but the factors are correlated 0.95, and reviewer 3 comes along and says, I think it should be 1 factor because correlated by 0.95 is too much. Okay, let's go from a 2-factor model to a 1-factor. That's like saying I'm going to force the correlation to be 1 instead of 0.95, and see if it fits, ... what's the word I should use? If I start with a model with more parameters and I take them away, if I simplify.
Not worse.
Not worse, yes. Worse or not worse in that case. So if you take something away, you can't make it better. The best you can do is not make it worse. And I know that that sounds backwards relative to how we're used to thinking about it, but in about a month, when we start talking about invariance and whether a factor structure is the same across groups or across occasions, that's exactly what we're going to do. We're going to let each group have their own version of the model, and then we're going to sequentially make it the same and see if we made it worse. If we made it worse, then that's non-invariance, and we have to figure out why it got worse. So it's the same ideas, just from the perspective of this is as good as it gets. Now let's see if we didn't break it. As an aside, there are a few cases in which you should use what's known as a mixture chi-square distribution for these tests rather than a standard chi-square. The one that you will come across in this class is testing that factor correlation against 1. Because a correlation can't go above 1, if 1 is your null hypothesis, then you can cut your p-value in half. So that would be a critical value of 2.71 for the difference in chi-square relative to 3.84. A very small difference. It's one of those things that people note, but in practice, I just don't care. I have too many things to care about, and that's not going to be one of them. Likewise, if you're adding, like in multi-level modeling, if you're adding a random slope and its covariance, the right critical value is 5.14 instead of 5.99. If you forget about this, you're being slightly conservative. Okay, I'm all right with that. But you will see that mentioned as an aside. So generally speaking, likelihood ratio tests is your way to compare alternative possibilities that you put forth, alternative HO models. If you want to compare a non-nested model, then that's not a likelihood ratio test. So there's very few examples in which this would happen in this context. One would be if you're not sure where an item should load. If you want to test if the model fits better if it loads on factor 1 versus if it loads only on factor 2, that's non-nested because both of those models would have the same degrees of freedom. In that case, AIC and BIC, smaller wins. And yes, it is entirely possible that AIC might get smaller and BIC doesn't, or something like that, and they might disagree. Here's one that I bet someone will mess up because it has happened every single semester I've taught this. Are you listening? Do I have everyone's attention now? Yeah? Yeah. This one. If you take items away, that's not non-nested. That's not comparable. So if you have an item that looks like it doesn't load very well and you want to just pull it out of the model, and that's not a comparison you can make. Think of it this way. The answer key H1, let's say that you have 8 items and you want to compare against a model that has 7. The H1 best model is on a different scale because it's an 8-dimensional matrix in one and a 7-dimensional matrix in the other. They're not the same. So their heights are going to be different because fewer stuff is getting added into it in the case of 7. So you can't make a formal comparison in that case. The correct way to do that is to keep the item in the model, but constrain its loading to 0. Then it's 8 and 8, and it's comparable. But you don't actually have to do a likelihood ratio test in that case, because each item's loading already has a wald test for it. Each loading has estimate, standard error, z, and then a p-value. That p-value will tell you if the loading is significant. So you would end up coming to the same conclusion if you just stared at that p-value than if you took the item and forced its loading to be 0. 0 is the null hypothesis. So AIC and BAC, if you're in that situation, no critical values. It's just smaller is better. So any questions on that idea? No? Okay. So how would you add in additional sources of correlation? Error covariances. So we saw this a little bit last time as a potential way that I could have fixed this dimensionality problem with the single factor model and the forgiveness data. Error covariances plug holes. That's what they do. So if you have, say, two items that are more related in the data than what your model says, you can allow those two items to have an extra relationship via a two-headed arrow between the two sets of E's. In the code, you would estimate, like in M+, it would be like if it's items 1 and 3, it'd be item 1 with item 3. That would give you an error covariance. In Levon, it would be item 1 squiggle squiggle item 3. Same thing. That's one choice. And if there's only like one or two items that have like just a pair that have a problem, that might be a reasonable thing to do if you can defend it based on their content or some other feature that they have in common. So a few of you had scales in which only like two items were reverse coded, and I made a note that said watch for those because odds are good. They're going to have an extra relationship just because of the way that they're worded. There was one person, I can't remember what the topic was, but they had like 6 items that all had the same stem and then 2 that were like binary or something. Who was that? Is that person here? This is what happens when you read like 27 homeworks in one afternoon. I don't know whose is whose, but I remember the story. But I remember making a note like, nope, because of those items having like a whole different thing about them, they're probably going to be related. In models that don't allow error covariances, so when we get into models for ordinal items or binary items, you can't do that. You can't do that if you have full information maximum likelihood. Because if you don't have residual variance as an estimated quantity, you don't have residual covariance as a choice. Instead, what you can do is estimate what's known as a method factor, which is another factor where the two items that you want to have a covariance would load only on it. And you would fix both of their loadings to 1 if it's a positive covariance that you want to allow, or one loading to 1 and the other to -1 if you want to have a negative extra relationship. So that's where bifactor models is the term that IRT is used for that. That's why they have them, is because you can't have error covariances. But the one thing that you have to keep in mind, though, is that you are changing the statement about your data. So if I have a single factor model and the only way I could make it fit is to add in 2 or 3 error covariances, I don't have a measure of one construct. I have one construct and some stuff. Because those relationships are some kind of multidimensionality that I don't know what it means. And if I have a lot of those, like if I have to add a whole bunch of error covariances to make it fit, that's a sign that nope, that model is just not tenable, and we need to reconsider how many factors we need. So we ended, I think, on this slide, the idea that these are all, if this is all that's in the model, these are all going to fit the same. But they make different statements, theoretically, about what the relationship is for, and they also then allow different opportunities for how you could use these latent variables in relations with other constructs. So in SEM, usually just measurement models isn't the point. Measurement models are like one step on the way to look at a bunch of stuff, but you would want to make sure that each latent factor is set up correctly before you estimate a joint model where there a bunch of factors are in there. So like the joint model that happens later would be dictated in part on what you choose here. So should we go back, should we re-go over this? Yeah, I like that phrase. I'm going to attribute that one. Re-go over. Re-go over. Not just review, but re-go over. Yeah. So here is the easiest one, the middle one, error covariance. So I have 6 items that are all supposed to measure some kind of social anxiety. These 2 have to do with public speaking specifically, and they have an extra relationship in his example that the single factor does not fully account for. Okay, so I would rationalize this by saying, well, these 2 items are about a particular facet of social anxiety, which is getting up in front of people and talking, so that's why they have that relationship. Seems reasonable. Fun. An alternative would be something like, no. Well, this is not just something I have to deal with as a problem. This is an opportunity. All problems are opportunities. So I could blow this up essentially and make it its own thing. I want to now try to measure individual differences in public speaking anxiety specifically as a separate trait. And I understand that people who are afraid of speaking in public probably have some degree of social anxiety. They tend to go together, or at least the person who put these items together must have thought so. So in this case, I'm not relegating this extra relationship to an error that I'm just trying to get rid of. I'm making it a thing. And so long as I have a covariance between these two factors, then even though this second factor is locally under-identified by only having 2, I can still get away with having the loadings be different potentially. But I have seen this blow up in practice, and if the model blows up, this is the problem. You may still have to force these 2 loadings to be equal, in which case you've literally just taken the correlation between these 2 and drawn a circle around it and called it a thing. So this model is very different in terms of what the factors are supposed to mean than the one on the right side, even though they're both 2-factor models. The difference is which items contribute to which factor. On the left side, only the first 4 items are indicators of social interaction anxiety, whereas on the right side, all 6 are. So social interaction anxiety is being measured in the original intended way by all 6 items. And then this thing, which he has labeled public speaking anxiety, which if I were writing the book, I would call it something else because it's not that, is whatever is left that's not social anxiety. So people who don't have social anxiety but who don't want to talk in public, right? Like that idea, that it's something else. Or people who talk really loudlier than I do out in the hallway. Not fair. Let me reload my voice and try to talk even louder. See, I'm the opposite. I have no problem speaking in public, but if you get me at like a party where I'm supposed to stand around and make small talk, I'm terrified. Seriously, that's how I roll. Yeah. And I'm not the only methodologist I've met that's like that. I once had a class that I took from someone, and the professor, like you could see just me sitting in his office, he was terrified, like turning bright red and just like shy. But then I asked a question, and it was like a light bulb, and he picked up his marker and just started writing and gesturing, and he was like in his element, right? Like that's me. So if you ever see me like out in public and I'm all like, don't talk to me, don't take it personally. That's just my social anxiety.
And don't talk to me.
Yeah, and don't talk to me. No, just talk around me, and I'll smile and nod, but then I'm not like on the spot. So anyway, point being, whatever this is, it has nothing to do with this. And it has nothing to do with this because of what's not here.
Correlation.
Yeah, these 2 are orthogonal, uncorrelated. And they actually have to be, otherwise this thing is going to break, because these 2 items are loaded on both. So this is conceptualized as either a method factor or a bifactor or a specific factor. Like there's some other label that is like, it's not this, it's something else. So it would be very tricky, I think, in practice to have this as a predictor or an outcome of other things because you don't know exactly what it is. It's something that is uncorrelated, but yet still measured by these 2 items. Okay, how are we doing? Good? All right. So this last one here is for folks that are like, but my hypothesis says that social anxiety predicts this other stuff, and I don't have room for 2 different kinds of social anxiety in my theoretical model, and I only want 1. Okay, well, let's put them back together again through this higher order factor. So this is Unit 8. We will explore these in greater detail. So this is, rather than having a covariance directly between the 2, I have operationalized that covariance through a higher order latent factor, as it's called. So this idea of a circle predicting circles, it's either second order or higher order is the way we talk about that. Because there's only 2 underneath it, though, what do we have to do? Yeah, fix the loadings equal to each other. So either the loadings are both equal to 1 and the variance of the upper factor is estimated, or the variance of the upper factor is fixed to 1, and these loadings are estimated, but estimated to be the same number through a constraint. So that would be a constraint we put in the program via labels. We would label these 2 paths as the same, and then it would figure out what number best fits both. But this model with the two factors that have a correlation is the same because the correlation is essentially just induced through this higher order factor. So you've taken the correlation between these two things, given it a name, and drawn a circle around it. And now you're back to general social anxiety, which is what you wanted in the first place. So there's not necessarily a right way or a wrong way, but I think it's important to acknowledge that all four of these pictures represent multidimensional solutions to some extent, just in a different way of thinking about it. Okay, questions or comments on that? Did I shame them away? I think I did. Maybe. I'm not loud enough to shame anyone, damn it. Got to work on that. All right, when to simplify. So in the textbook, he pulls a number just out of the air. 0.85-ish would be when you might say, is this really two things? And I don't know that there's a whole lot of literature on that, but yeah, if you start to see really high correlations, it might be reasonable to test one factor instead of two. Pulling back the previous slide for a minute, the size of the relationship between these would also dictate the extent to which this higher order model makes any kind of sense. So let's say that social interaction anxiety and public speaking are only correlated like 0.2. Then their common variance is 4%, and that's what would go up here. So I would find that model probably not useful because you're combining two things that really aren't that much related. Whereas if these are correlated 0.9, okay, yeah, like let's just put that into one thing and call it good. So if you have a two-factor situation where the correlation is super high and the model fits worse if you make it into one, that would be an argument for something like this, where you can still think of it conceptually as one, but you are representing the fact that it's not just one factor. Dropping an item is tricky. So if an item has a negative loading or a zero loading, that's an indicator that you don't need it. No questions there. Sometimes when you look at the local misfit, you might find that one item is like the source of all the problems. Like it just doesn't match any of the other items, and you might choose to dump it just because of that. One thing to be careful about, though, is that anytime that you're dropping an item that does have a sizable loading, you're potentially lowering your reliability. So that would be, do I want to have less reliability but a factor structure that's tighter, or am I willing to have these additional collinearity issues sort of buried in there at the expense of keeping this thing? Keep in mind, if you drop items, it's not comparable directly. So you can say that the 7-item model fits and that the 8-item model doesn't fit, but you can't say that the 7-item model fits better, for instance. What to do? Let's see here. You may see this error message, non-positive definite. Have you heard these words before? It means that something went wrong, that the determinant is too close to zero in matrix terms. In real life terms, it means model is broken, can't keep it. It means something went out of bounds. Usually, it means that in the standardized solution is where you would see it. A loading went over 1, a correlation went over 1 or below -1, or a variance went negative. So it decided that the numbers that made the data the tallest are somehow out of bounds relative to what they should be. You can't keep it. So in that case, check to make sure that you haven't missed a step. So make sure that every factor has a mean and a variance, that you've scaled it, that it has at least 3 items. Make sure that your marker item does load on the factor. And empirical under-identification could still happen, in which case you may have to make more constraints or reconsider what you want to do with respect to your indicators. It's harder to give general advice about that, though. And open and in case of emergency, there is a section in your textbook that he refers to as E/CFA. So if you are handed a data set where, for whatever reason, you really have no idea how many factors are supposed to be there, like you just, it's not your data, maybe it's in another language, don't even know what the items mean, like if that happens, could happen, right? then you could fit an EFA-like model, but do it in this framework. So in that case, you could start with, say, maybe, let's go 4 factors, I don't know. And you would fix each factor to have a scale. Each factor would have one item that loads only on it, and then you would let all of the items load on all the factors otherwise. Then you could look at the pattern of what happens in terms of which loadings are significant, which ones are positive, which ones are negative, and that could help you sort of guide your way towards some kind of solution. So that, I think, is a more useful suggestion if you really have no idea what you're looking at than going back to EFA. Because the problem with EFA is that different rotations and different solutions are not defendable on the basis of empirical data. You could say, I think it has 3 factors and it's quatramax, and someone else is like, no, I think it's 4 and it's varimax, and you're both right. All right. So we've talked about fit, but we're not done yet. We have to talk about reliability and effect size. Because just because a model fits does not mean it's useful. So some bad news. What if I had these 2 potential correlation matrices? I have 4 items that are all correlated 0.1 versus 4 items that are all correlated 0.8. A single factor model is going to fit both of them equally well. Is that surprising?
It is.
It is. Because when people think fit, they think like goodness or utility or usefulness, and that is not what fit means. Fit means that your factor structure has replicated the patterns in the data. It says nothing about whether there are any patterns worth replicating. So you could have variables that are completely uncorrelated and do a really great job at recreating those 0 correlations. Your model would fit well. So I've answered this question from people who should know better. Various folks who've been fitting these models for years. For instance, I once had a faculty member come to me with a factor solution, had excellent fit. None of the loadings were significant. The question is, how can it be? So I told this person, your model has perfectly recreated the non-relationships among your items. You don't have a factor. They're not measuring something in common, then there's no point to doing this. So if your items aren't correlated, game over. So that'll be one of the very first things I ask you to stare at your own data is a correlation matrix. If you don't see at least something there, there's not much point in moving forward. If the items are supposed to measure something in common. So whether the factor is measured well is a separate concern from whether we have 1 factor at all, or 2 factors or 3 factors. So we can think of this as effect size for the individual factor loadings, or we can think of this as reliability because they're computed using the same information. So practical significance is given by the standardized factor loadings in that correlation metric. Higher is better, up to 1. If you take those standardized factor loadings and square them, what do you get?
R square.
R square, yeah. If the loading standardizes R, then you square that and it's the R square. So R square in this case is a little bit tricky because people like to think that R square is the proportion of variance that's explained. I can't use that word in this class. I couldn't use that word in the other class for the same reason. What I would say is that R square is how much of the variance is attributable to the factor, how much of it is thought to be true score variance, but I can't say explained because I still don't know what caused the true score variance. I don't know why some people would have a higher F and some people would have a lower F. I don't know that. That's not the point. So I can say how much of the item is attributable to the factor and how much is not the factor. And that's what R squared would tell me. So I explained makes me squishy. You know, that's my phrase. Like squishy is like a word that means uncomfortable. Like if you're staring at someone like getting their COVID shot and you see the needle go in their skin and you're not a nurse, doesn't that make you feel squishy? Just me? Or like if someone opens the toaster on the floor and you put your bare foot into a pile of crumbs and they stick to your skin, squishy. Crunchy in that case, but also squishy. So squishy means uncomfortable. But explained variance when we're talking about a latent factor that's not a thing, not explained. But what we do want to know is how reliably it's measured, though, which the loadings contribute to. Go ahead.
So yeah, in this case, we will have as many R squares as indicators we have for the factor, yeah?
Yep, each indicator gets its own.
Can we have something more general?
What a great question. Like for the factor?
Exactly, yeah.
Yes, we can. So let me get there. Yes, we can. That's reliability for the factor. Yes, that's where I'm headed. So first we have to make sure that our model makes sense. So in addition to all of the not having a non-positive definite, but we want to make sure that all the estimates are within bound and the predicted item responses are plausible at plausible values of the latent factor. So here's an example of when this might not work. These are real data. These are data that were collected in an item response format that was a continuous slider bar. Have you seen these before? Like Qualtrics has this item type, and a few other places I've seen it where, like, rather than picking a number that says, you know, how much do you agree, 1, 2, 3, or 5, you move it. And the idea is that it's supposed to be more continuous and have more variability than just having like an ordinal scale. It also works for people who are nonverbal or like when language is an issue. So this is, these are data from a study measuring students who have disabilities, and they were asked various questions about how much they agree with this. And this is an item, a lot of the items looked exactly like this, where most of the people agreed 100%. Well, this is continuous. I'm not going to argue about that, but is it normal? Decidedly not. But it's not ordinal. It's not categorical. It's not a count. Like, what do I do with this thing? Clearly, I have a boundary problem here. And that shows up. This is a little picture that the ingredients for making it are part of the spreadsheet that goes with example 4. What I did is generate a regression line for each of my items based on their intercept and their factor loading in the unstandardized solution. I just put it in as the regression model that it actually is, and I treated the x-axis as plausible ranges of my factor score in a z-score metric. So this is plus or minus 3 standard deviations on the latent factor, and the y-axis shows the percent of the scale that is predicted at each of these points on the latent factor where the scale only goes up to 100. So it's 0 to 100 is the ends of the scale. So if we go down here, people who have very low levels of whatever this ability is would have predicted values ranging from 20% up to about 50%. But then we follow the lines and, right around plus 1 standard deviation, what happens? Where do my lines go? This is a softball. Above the possible score, out of bounds. Because this is a linear model that doesn't understand that it needs to shut off as it gets towards the endpoints. So those of you who had generalized models with me, what do you think we need to do to fix this? Link function, ideally. Turns out link functions for this type are something that you'd have to program yourself because it's not built into software very easily. I know. Bayesian folks, knock yourselves out. Do you know what I did? Transform it. I made it into that. How did I do that, you ask? I'm glad you asked. This equation. So I transformed it via what's known as a logit transform, where I have the value minus the low divided by the upper value minus that one, and then I took the log of that. So this part turns it into a proportion ranging from 0 to 1. I take the log of it, and it becomes a logit. So then I fit the regular CFA factor model to the logit version of this outcome response. And this is the prediction that it makes when you back translate into the original metric. It understands that even though the factor keeps going up and up and up, the highest this can go is 100. So I'm not saying that this is the best idea, but if you have data like this, this is definitely not the best idea to let it go out of bounds. And here's a paper that was recently published doing it a better way using a beta distribution and a logit link function. It's not a logit because beta doesn't have zeros and ones. It's something that's like the middle part only. But there's a reference for you if you're interested in analyzing this kind of slider bar data. And I believe Alfonso is working on a project involving beta distributions too. Is that right? Jonathan's folks?
I don't know.
He did at one point. I want to say he presented a poster on this at SMEP last year. But so you can ask him about that. Alfonso Martinez, fellow graduate student. Nathan says, "You transform the data." I know. Sometimes I get a little lazy. Because that way you can use the regular CFA model. But the point, though, is like looking for this problem of going out of bounds. That's your indicator as to when CFA is not a good idea. And none of your model fit statistics are going to tell you that. Because model fit is predicated on the idea that the only thing we need to track is means, variances, and covariances, because that's true if the data are normal. If the data are not normal, then there's higher order moments of skewness and kurtosis and stuff like that that we should have been tracking the fit to, but we're not. So you can have a model that fits great that makes implausible predictions like this, and I would argue that's not a good enough model. So this will also be one of the things I ask you to do with your own data, is to see if it goes out of bounds. Because that's the best answer I can give, is when you need to switch to an ordinal model that understands the bounds. Okay, so to answer your question, is there a way to talk about sort of a generalized effect size? And yes, there is. So I want to show you a couple different kinds of reliability. So one way of talking about it is information, which, yes, that's the same information IRT folks that you learned about, and we will see that in about a couple weeks. The problem in CFA with information is that it's essentially redundant with standardized loadings. That's why no one computes it and no one cares. The standardized loadings tell you the same thing. But the idea of reliability can be operationalized two ways. One is omega. This is your alternative to alpha. So alpha assumes what three things? Do you remember? Unidimensionality.
Tau equivalent.
Equal loading, tau equivalence, yep.
Constant error.
Constant and
uncorrelated error.
uncorrelated errors, okay? So omega is reliability for a sum score. So this is the expected reliability if you took the items from your factor model and added them up. Your factor model should have already given you evidence that they are in fact unidimensional. So in the sense, omega still assumes that, but we checked it, so we should be good. So we would only do omega per factor. Otherwise, it doesn't make sense. But what about the tau equivalence part? Right here, we put the loadings in. They don't have to be the same. And what about the uncorrelated errors part? It's in the denominator. If we had to put error covariances in to make it fit, we got to put them in the formula. And they count against us. Because the total variance across items is not just the sum of their variances if they're related. It's also the covariances among the items too. So they show up in the denominator. So it's the variance of the factor times the squared sum of the unstandardized loadings. That whole thing goes in the denominator and gets added to the error variances plus any error covariances. So conceptually, it's true over total. The same idea of reliability, just building in the model parameters as part of it. So in your methods section, this is what I would give them. I would give them omega if you're planning on adding items up and working with sum scores. Another one is factor score reliability. This one I have not seen discussed as much as omega, but it's an alternative, particularly if what you're going to do is output factor scores and treat those as your observed variables instead of sum scores. And that is computed as the variance of the factor divided by that plus the squared standard error that goes with the factor scores. So we have to dig through the output and request that as a particular piece of information. So it's still the idea of true plus error, but measured in a slightly different way. So here is some code at the bottom as more of an FYI. If you are in a situation where you have so many constructs to be measured and not enough people, that you have to take these shortcuts, that you have to somehow represent your constructs as observed variables rather than latent. That may happen. There are ways to correct your observed variables for the unreliability that you know about, having fit them to a factor model. So this is code in M+ in the first part, and then Lavon and R in the second. What you would do is create a single indicator of a latent factor and constrain its error variance to the amount of its variance you know to be the unreliable part. So this is in your textbook as a potential alternative to pretending that your observed variables are perfect. And in that case, depending on which version of the observed variable that you use, you would use that version of reliability. So to recap, omega is reliability for a sum score. If what you're planning to do is test your factor structure, verify that it works as it's supposed to, and then add your items up, that's what you would report omega for. However, adding items up is inconsistent with the factor model. Adding items up is a parallel items model, which we haven't gotten to yet, but it's coming very soon. Alternatively, if you were to output a factor score, so the best guess as to what each person's F would be, then you could use that as an observed variable and correct for its unreliability using this formula instead. But these are two-stage shortcut things you would only need to do if you can't do the proper simultaneous analysis. The goal of this should be to keep everything latent. It's just that's not possible sometimes, given the complexity of what people want to do. So that's your answer as to an overall estimate of sort of goodness or effect size. It would be captured this way. I think. Okay, yeah, we made it. We're almost there. Woohoo! Question?
If it's a sum score, does that require no missing data then?
If it's a sum, no missing data, yes. If you say, okay, I'll just take the mean, then you are assuming missing completely at random for any items that are not part of it. But sum scores are the same thing as fitting a parallel items model, which we have not done yet, but which I'm about to do.
Great.
Great, she says. Not at all sarcastic, right? Great.
No.
Not at all.
I'm excited.
Yeah. So one of the articles that is on your reading list, so I told you I would try to emphasize the ones that are like relatively more important. McNeish and Wolf 2020, I say. They basically explain either via examples, via simulations, via math, that the only situation in which you would come to the same conclusion using a latent variable versus a sum score is if the parallel items model fits, which means not just unidimensional, not just how equivalent equal loadings, also equal error variances. So if you add items up, that is the model you are fitting without realizing it. The extent to which that's a bad idea depends on just how far away from those assumptions your data actually are, which is, say it with me, an empirical question. Always. So let's look at what happened to my forgiveness scale. We found that the two-factor model fit, and I was satisfied with that. Now, each factor only has 3 items. How reliable do you think each factor is going to be? 3 is enough to like make it go, but is that enough to really give you a picture of someone's ability? Probably not. Let's find out just how unreliable those 3 items are. So I know what I needed. That's why I was on this page. I'm going to make the programs do math for me through labels. So we looked at this a little bit last time. I have fit 2 factors. I called them sit P and sit N for positive wording and negative wording. And I labeled each of the loadings that's being estimated as label L1, 2, 3, L4, 5, 6. I also labeled the error variances, 1, 2, 3, 4, 5, 6, And the reason that I did that is because I'm going to use those estimates and make it do math. So model constraint in M+ is a command that is used not only to make constraints, but also to make new combinations of estimated parameters. Unlike lincom in Stata or estimate in SAS or things in R, they can be linear or nonlinear. You can do any kind of math that you want on them. So I am making two new quantities. I'm calling them omega p and omega n, one for each. And I am putting into the formula the labels that correspond to the parameters to be estimated. So M+ is going to read this and go, oh, she wants L1 plus L2 plus L3. So I'm going to go find whatever those loadings turned out to be and plug those numbers into the formula. So it's doing math on the results for me. So here is the sum of the squared loadings. The one out front is a reminder that the factor variance goes there. Divided by that, plus the sum of the error variances. And I have a note here, don't forget the error covariances if you have any cough, cough homework question. I didn't have any in this example, but you will, because they go into the denominator as well. In Levon, I have the labels multiplying each of the parameters out front, and then linear combination, or computed quantities, I'm going to use that phrase deliberately, is colon equals. That's how you make up a new thing using the parameters that you already have. And so I am defining my two omega coefficients with these two combinations. I believe people have made R packages for this. I want to say SEM Tools has an omega in it. I haven't played with it enough to know if it matches exactly or if it's some other version of omega, but there may be ways that you can do this with less code if you're so inclined. But I think for the purposes of instruction, it makes sense to go ahead and compute it out like this. Okay, questions on that much? Yes?
Those are the unstandardized version, right?
Yes, they are.
Okay.
Yes, that's why we have to have the factor variance as part of the formula.
Okay.
So that's why I have that in there to remind you that if you have an estimated variance, that it needs to go in there. So then in the parameters that we get back, here's our model. In M+, at the end of your unstandardized solution, there is a new section called new or additional parameters, and there they are. So my omega for the positive worded items is 0.74, and for the negative was 0.78. And alpha, by the way, was 0.75 and 0.78. So these, in this case, it wasn't actually that far off. Probably because there were no error covariances. That seems to be the thing that makes it different. Now, is this good enough? I asked you this question like a month ago. Do you remember? Yes, it has been that long. This is week 6. I know I'm not supposed to remind you of that. Like, what was a good enough alpha in your fields? Remember?
Alpha?
Yeah.
That was all over the place.
0.8, 0.7? Not below that, though, right?
Sure.
Sure.
I have seen articles that have been published with lower.
Okay.
My advisor would never.
Would
let
never.
me get away with that. My HISA advisor.
Yes. Well, if it's lower than that, they better at least put a caveat somewhere that says results may be squishy because of low reliability or something, right? So this is marginal to acceptable depending on your field, okay? This number. But what does this really mean? I'm about to blow your minds. Seriously. I think so, at least. When I computed this for the first time, my mind was blown. Here's the Levon output in which the new, it's called defined parameters, and the numbers are spot on. So by making the computer do the math for you, not only does it do the math more accurately than typing stuff into Excel, but as a benefit, you get a standard error that goes with it. And that's something you would want to report as well. So we looked at the remaining misfit, decided it was good enough. Now we get into standard errors, because that's actually what the reliability coefficients are translating into. How much of the variance is error, And if I take the square root of that error variance, that's my standard error of measurement, right? So m plus gives this stuff to me. Come on, there we go. I lost it. There we go. So this is the end of the output when you ask for factor scores. It gives you summary statistics about your factor scores. So this is a covariance matrix that includes the factors and their standard errors as entries. So SIT P, according to the factor scores, has a variance of 0.777. The factor score variance is lower than it's supposed to be. That is also true for negative, although to a lesser amount. That will happen. The term for this is shrinkage. Whenever you output quantities, they will have less variance than they're supposed to, because extreme values get pushed towards the middle. So that's one of the reasons why you don't want to output factor scores unless you absolutely have to. I'm doing this more for descriptive or pedagogical purposes than to use them in anything. I also have, where are they? The means at the top here. That's where the actual standard errors are. So the standard error of measurement for my positive situation forgiveness factor is 0.47. One number. One standard error, no matter what your factor score is. Coincidence or consequence?
Consequence?
Consequence. This is a linear model.
Yeah.
So another way of saying that is that if an item's good, it's good for everybody, and all the items are equally good for everybody. And equally good translates into equal reliability that is constant across your latent trait. So it's one number that's supposed to describe all of the uncertainty equally across the factor scores. Probably not the case, but that's the assumption that we're making. Same thing with negative situation. It's a little bit smaller because its omega was a little bit higher. Its omega was a little bit higher because its loadings were a little bit higher. So is this a good number or a bad number? This is the mind-blowing part here. Standard error of measurement, what would we typically do with that? Build a confidence interval around a score, maybe? So let's say that I'm trying to predict a confidence interval around someone of average forgiveness, right at 0. So 2 standard errors on either side. I'm going to make the math easy and say it's like negative 0.8, actually negative 1 almost, positive 1. So my range of expected values is like most of the number line for what the range of this factor is. So somewhere within plus or minus 1 standard deviation is your score. Isn't that nuts? That's bad, right? Because that means somebody that we think is at 0 could be anywhere from minus 1 standard deviation below to minus 1 standard deviation above. Like, that's a huge range. Like, that's the whole range of the factor almost. Like, 67% of our people are going to be plus or minus 1 if this is normal. And that's all the best we can do to say where someone is? So I'll ask you again, are these omegas good enough? Yeah. If the best we can do is, I don't know, you're somewhere around the number line. Somewhere on the number line, that's where you are. So standard errors, I think, make it more real. Like if I were going to make a decision about somebody and take into account the imprecision of measurement, that makes my decision a lot harder. Here are my factor scores, by the way. I made a nice little histogram. This is something that came out of M+. To make it come out of M+, I think I wrote this down. Yes, I did. Here are the directions for how I found that in the plotting menu. Does this look normal to you? Like half of it does, maybe. That's positive situation. This is negative. They both have the same sort of pattern to them. What about the top end? There's a term for that when everybody's shoved up against the boundary. Starts with a C?
Ceiling effect.
Ceiling effect, yeah. Do you know who these people are? These are the people that said 7 for everything. We don't know how high they are. We ran out of room. We don't have the information in the scale that it would take to pull these people apart. The only reason we have a factor score at all is because of the prior, yes, that prior, that we're putting on this to make the factor scores using Bayesian. It's a Bayesian prior saying that the factor scores are supposed to be normal that allows us to even get an estimate for people who have like a perfect response pattern, either the lowest or the highest. So we top out around like 1.2 or something. That's as high as this goes. And if I plot the predicted item responses from my 3 positive items and my 3 negative items given the model, lo and behold, it goes out of bounds right around the spot where it levels out. That's not a coincidence. So just because the factor scores are supposed to be normal doesn't mean they're going to be. It is a consequence of what kind of items you have and how much information they have in them, how good they are in terms of their loadings. So to make this better, I would need to find items that are harder to endorse. I would need to add items where even the most forgiving people would not pick 7. So this would be what I would look at to decide, is 7 categories enough for a CFA? I don't know about that. We start to go out of bounds at about 2 standard deviations above the mean in both of these cases. More fun with factor scores. Here is the correlation between the mean of the positive items and the factor score I outputted. It's 0.98. And I think this is why you still see some scores. Because as long as you have a single factor model where the items load reasonably well, you're not usually going to come to that different of a conclusion based on the mean across items versus a factor score. But to the extent that your items aren't unidimensional, to the extent that the items don't behave like you're supposed to, that's where you would start to see more problems. And here are the differences in correlation between positive and negative items if you just use the sum scores, or mean scores rather, versus the factor scores. We get 2 different estimates for their relationship as well. All right. So did that blow your mind a little bit? Just a little bit? Yeah, so that's what I would look at in deciding whether, like, what's good enough for reliability is, okay, what kind of standard error does that translate into, and can you live with that in terms of your purpose of measuring people? Last but not least, do we have the strength to look at like one more thing? Can we persevere on this Thursday afternoon? Zoomers, can we persevere? See if they respond. Are we persevering? Oh, yes, we're persevering. Excellent. So let's test the idea of whether tau equivalence holds, parallel items holds. We can do so using labels as constraints. So our last little piece here, model 5, is still the 2-factor model, but here's what I did. Rather than have L4-L6, meaning that I've labeled each of the separate loadings, I put one word there. The word that I put is to remind myself what I'm doing. So I typed neg load, because I'm constraining these 3 loadings to be the same. That's what this is doing. So anytime you use the same label for multiple things, you are telling it, hey, make all these things the same number. Go figure out what that number should be, but make them all the same. So that's more explicit in R, the way that I had to type neg loading in front of all 3 of those things. And there might be a faster way to do it, but this is the way that I know how to make it work. So how would I guess if this model is acceptable? What do I need to do? Likelihood ratio test. How many parameters have I saved through this constraint? 2, because I went from 3 loadings to 1. So if the test is significant, have I made the model better or worse?
Not worse. Worse and not worse.
Yeah, this is a worse, not worse. If it's significant, that means worse. So in the results then, There's the proof that it did what I wanted it to. This is our output, by the way. So all three of the unstandardized loadings are the same. Note, however, though, in the last column, standardized are not the same. That is as it should be. What else goes into a standardized loading that I haven't constrained equal yet? The error part. Yeah, so the errors are all still separate. It's just the loading that's the same. That's why these standardized loadings still differ from each other, but the unstandardized do not. So the three negative items have three different error variances still. So here is a comparison of the two fits. The difference in degrees of freedom is indeed 2. Here is the ANOVA output from R. Chi-square difference of 34 on 2 degrees of freedom is significant, so yeah, that's worse. What that means is that a model where these are 3 different numbers fits better. They're not equivalently discriminating. Okay, let's try the other. Positive loading. Same thing. Now I am also adding labels for the errors because, by the way, if I estimate reliability assuming that these loadings are the same but allowing the error variances to differ, that is alpha. So I'm getting Cronbach's alpha through the factor model because I've put the assumptions that alpha makes into the model. One factor, equally discriminating. No error covariances. So 3 loadings down to 1. Those are my 3. Survey says, okay or not okay? Chi-square difference is 2.6 on 2 degrees of freedom, p-value of 0.27. Not worse, which means good enough that I could make them the same. So that would mean that like alpha or omega would be acceptable because the assumptions underlying alpha hold in this case. Well, let's go one more further. Can I make the error variances the same too? And this is another version of reliability known as Spearman Brown. This is also the version of reliability that you would have to use to anticipate how much your reliability would grow if you add more items. Spearman Brown prophecy formula, does that sound familiar? Yeah, this is the basis of it. The assumption you are making is that the items are equally discriminating and the amount of not the factor variance in them is the same. So we test that, and now the unstandardized loadings are all equal and the standardized loadings are all equal because we held the errors equal. So another way of saying this is that all items are equally reliable because we've fixed both parts, the factor part and the error part. But survey says, wah, wah. So no. So that means not the factor variance is different. And here's all my words. So when you are doing your homework 3, I am giving you permission to take my words. Okay? I'm giving you permission to start with these words and change them to meet your plan. So like a lot of this is just boiler text. Like I would just plug this paragraph into a manuscript. Like this just describes the process. You would change like how many items you have, what you're measuring. So that being said, I want to give this to you as a template that you can use to start with. But if I read your homework and I see the word forgiveness in it, I'm going to be mad. Fair? Mm-hmm. Like Control H, find and replace, forgiveness of situations with, conspiracy theories or whatever I'm measuring this week, right? So I do expect your text to deviate to the extent that your results turn out differently, but you can start with this as sort of a way of talking about things. And the rest of this I am not going to do in class. What I am going to do is make a separate recording because this is for the benefit of the longitudinal class. And I want to show you that a factor model is another kind of alternative covariance structure. And you can fit it in SAS mixed. QED multi-level models are indeed psychometric models. So if you have a hammer, everything is a nail. It is indeed. So I will make a separate video about the rest of this. That way I don't have to bore the rest of you who don't want to learn about longitudinal in the middle of your measurement models class. Fair?
Yep.
Fair. Okay. Questions before we call it a week? No? We're calling it a week? At least I'm calling it a week with teaching. I know we still have one more day to go. But, all right. Then have a good weekend. Let me know if you need anything. Thanks for being here.